Module 15b, I want to start talking about the rates of the reactions themselves. You do need to understand the difference between an average rate and an instantaneous rate. If you're given the appropriate experimental information, you should be able to determine the average or instantaneous rate within a reaction. Be able to understand and use the term rate constant and know the units associated with the rate constants. The units are dependent upon the reaction itself. So the units on rate constant will vary depending on that reaction. You should be able to use the rate law, which we also call your rate equation, to calculate the rate constants, or reactant concentrations, and determine the overall and order of reaction and the order of reaction with respect to each individual reactant. So average rate versus instantaneous rate. What am I talking about here? Well, consider a typical reaction. We have A going to products. We can express this reaction as rate equals negative delta change in concentration of A over delta T, as we talked about in the previous section. But if we say the slope of this line, we know slope is rise over run. So change in Y, concentration, over change in T, or change in X, change in Y over change in X is the change in the concentration of A over change in time. The reaction at a given time is equal to the negative of the slope of the tangent, or instantaneous rate. So again, average and instantaneous. An average rate is the change in concentration over a specific time interval. If I took these 2 points, and we'll show this again on another graph in a slide or two, but if I took these 2 points, these purple points, here, do this so you can see the color, here and here, and I took the change in concentration of A from here to here versus the change in time from here to here, that would be the average rate. But the instantaneous rate is defined as the negative slope of the line tangent to the curve. And this is at a specific point in time. The biggest thing is, if I took the concentration here and here versus the time here and here, the slope of that line would be different than the average rate because the reaction is changing as I go through. As I react more, the rate of reaction is changing. So if I took the concentration of A up here versus the concentration at the end, and I took the average each here to find the average rate of this slope, that's different than the tangent at a single exact point. So from the graph, when the concentrations of reactants decrease, the reaction rate decreases as well. Why? Why is my reaction rate decreasing as the concentration of the reactants decrease? Why is the slope of this line more pronounced than the slope here, or say the slope here? I have less reactant, right? So as the reaction progresses, there's less concentration of reactant, therefore the reaction naturally slows down. The instantaneous rate is looking at that exact moment in time. What is the rate? The average rate is over a specific period of time that we have defined that we want to look at. So concentration versus time. Let's look at this reaction. 2 moles of NO2 reacting to produce 2 moles of NO and 1 mole of O2. We see here on our y-axis we have concentrations of each species, and on the y-axis we have time in seconds. The green line here is the concentration of NO2, shown up here. That's what I was looking for. Let me find a color that you can actually see on this graph. Let's see. Let's try hot pink. NO2, the blue line being NO, and the pink line here being O2. What we see here is that the NO2 concentration is decreasing over time. The NO concentration is increasing, the O2 concentration is increasing. Valid, right? If we start at time 0, we only have NO2 present. We don't have any NO or O2 present. Again, valid. We see that the rate of production of NO is twice that of O2. Again, we produce 2 moles of NO for every 1 mole of O2. So all of this makes sense. But what I want to ask is some questions here. First, is the rate the same for each species as time goes on? And why or why not? Well, the answer here is no, it's not. The NO2 is reacting, so it's being consumed. And if you look here at this curve, the green line here, this line here, as I'm reacting it, it's slowing down the rate. Less and less is reacting as more and more, or it's reacting at a slower rate as more and more of it's reacting, so there's just less present. We're going to talk about it again near the end of the chapter of the collision model, how do reactions actually occur. These particles must come together. If there's less particles in the solution or in the mixture, then it's going to react at a slower rate because it's just less likely for them to be able to come together and actually react. I've also got 2 moles of NO being produced for every 1 mole of O2 being produced. So it's happening at a faster rate. Why is the incline of the O2 line, the bottom pink curve, so much smaller than NO? Because the O2 is being produced at 1/2 the rate of your nitrogen monoxide. What was the original concentration of NO2 at time 0? Time 0, up here, 0.100 moles per liter or molar. What is the original concentration of NO at time 0? NO is my blue line, and I see it is at 0 molar. We don't have any at the start of the reaction. Is molarity the only unit that could be described for using these gases? No, we could use pressure because we're using gases. Pressure can be measured as well. But again, I want to talk about instantaneous and average rate on this slide too. So let's talk about NO first. So I'm going to erase anything I've written on here so far. If I talk about NO, let's say I want the average rate. I start out here at 0.01 molar, and I end down here somewhere between 0.0025 and 0.005, closer to 0.0025. If I took the average of this value, the average X and Y here versus here, if I compared that, that would be the average rate of the entire run that I have. The instantaneous rate is what is shown here. I have taken 1 point on the curve and I've drawn a line tangent to that curve. I then measure the change in Y and the change in X, rise over run. This is my instantaneous rate. My instantaneous rate is the rate at that moment. I expect the instantaneous rate to be higher for reactants when I'm closer to the start of the reaction. I expect it to be lower for reactants at the end of the reaction. You can also see the instantaneous rate decreasing for the production of our products as well. If I took the instantaneous rate, say here or here, compared to where they are taken, the start of the reaction is just more pronounced. Instantaneous is when you take the slope of the line tangent to the curve. We draw a line tangent to that curve and determine the slope of that line. That is the instantaneous. It is what the rate is at that exact moment in time. So, average rate. Calculate the average rate of the reaction with respect to NO2 over the first 100 seconds. You can look at average rate at any sequence of time you want. You can say 100 seconds, 10 seconds, 400 seconds, whatever you want. But let's go ahead and do this. Let's look at the average rate of the reaction with respect to NO2 over the first 100 seconds. We know the rate is equal to negative 1/2 change in the concentration of NO2 over change in time. So plug in our concentrations. The concentration of NO2 at time 100, 0.0065 molar, and the concentration of NO2 at time equals 0, 0.0100 molar. We get a rate here of 1.8 times 10 negative 5. So again, all I did was plug in the data straight from the graph. And how do I know these values? Well, we talked about this reaction already. We can monitor the disappearance of that color of NO2 because it's a reddish brown color. We can monitor the production of O2 and the presence of O2 in the reaction. Both of those we can correlate back to the concentration of the other species. Instantaneous rate, though. Instantaneous rate means 1 instant in time. We use a concentration versus time plot to figure this out. Then you take the slope of the line tangent to the curve at time t, so at the time you actually want. The instantaneous rate, draw a straight line on the curve at time t. So example, draw a straight line that only intersects time at 100 seconds. And that's what I have here. This line, this is time 100 seconds, and the line that's drawn here is the line tangent to the curve at t equals 100. We find the slope of that tangent line and we substitute this into the rate equation. How do we find the slope? Well, it's rise over run. So we find the change in concentration of the NO2 divided by the change in time. We see we're starting at 0.005, or finishing the 0.005 molar is where we're finishing it, 0.0075 starting. The difference between there, or 0.0076, because that line does go just past 0.0075, I apologize. The difference there, though, being that 0.0026 molar divided by the time difference. We went from 50 seconds to 100 seconds. Is it? I can't read the graph that well. 50 seconds to about 160 seconds, I guess. Let me just look at the numbers they actually gave me. That makes it easier. 110 seconds. 160 minus 50 and 0.05 minus 0.0076. It gives me negative 2.4 times 10 negative 5. Again, the negative just tells me that it's a reactant. That's all it means. The rate here, plug that in for the concentration of NO2, and we get a rate of 1.2 times 10 to the minus 5th molar per second. How does the instantaneous rate compare to the average rate of the first 100 seconds, though? We calculated on the previous slide the average rate was 1.8 times 10 to the minus 5 molar. Here, we're calculating our instantaneous rate, at time 100 seconds is equal to 1.2 times 10 to the minus 5th molar. Does that make sense to you? Your average rate is looking at the first 100 seconds. Over the first 100 seconds, the rate was about had an average rate of 1.8 times 10 negative 5. If I look at exactly 100 seconds, though, at that exact instant, the rate was only 1.2 times 10 negative 5. Does it make sense? Hopefully you're saying, yes, it makes sense, because at 100 seconds has already passed. That's, 1 minute, 40 seconds? That's a pretty substantial time frame that's already passed. The reaction is already starting to slow down because a lot of the reactant has already been consumed and used up. So the instantaneous rate, the rate at that exact moment, is different than the average rate from going from 0 to 100. So we've got some different terms here we need to understand. Within rate laws, we've got your differential rate law and your integrated rate law. The differential rate law is what I refer to as rate law, and it's just generally referred to as the rate law. That's the rate versus concentration data. I look at the rate of reaction, I compare that to the concentration of the reactants and or products that I'm looking at, usually comparative to the reactants. The integrated rate law is concentration versus time data. We do some cool calculus, and we're not going to do the calculus in this class. We're just going to remember the three equations for zero order, first order, second order. But there's calculus involved to integrate these reactions so that we can actually talk about the concentration of these species with respect to time. So if I look at the reaction, A moles of A reacts with B moles of B, giving me C moles of C plus D moles of D, the rate law takes the form, rate is equal to negative, I apologize. This is your rate. That's what we've learned about previously. The rate law here, I thought I caught all these. The rate law is actually different than this because you need to know how to write rate laws. So rate law would be written in the form rate is equal to K, our proportionality constant, times the concentration of A raised to some value M times the concentration of B raised to some value N. K, your rate constant, is dependent only on temperature and the presence or absence of a catalyst. The units on K vary for the rate you have. M and N are proportionality constants, and they are experimentally determined. But this form of the rate law, you need to get very comfortable with because you're going to just be determining the rate law of many reactions with this form. Also, just generally speaking, the bigger that value of K, the faster the reaction goes. So what is a rate law doing? Rate versus rate law. Rate is when I talked about, the change and the disappearance of a product over, reactant over time, appearance of product over time. The rate law, though, shows how the rate depends on the concentrations of the reactants. So again, A moles of A reacting with B moles of B to give me C moles of C plus D moles of D has the rate law. Rate is equal to K times concentration of A raised to X times concentration of B raised to Y. Again, K is your rate constant. X is referred to as the order of reaction with respect to A, and Y is referred to as the order of reaction with respect to B. These exponents in your rate law are experimentally determined. They are your order of reaction. They are not the coefficients on the reactants. They may match the coefficients on your balanced reaction, but that's coincidental. They are not the same, and they must be determined experimentally. The sum of the exponents is called the overall order of reaction. We will do examples so you see how we find this information and what I mean by this overall reaction as well. The rate law, again, the rate law X and Y values must be determined experimentally. They're usually small integers, but they can also be zero or fractions. So what is the relationship between the coefficients balanced equation, the exponents, and the rate law? They may or may not be the same, but it's coincidental. We have to choose conditions where the reverse reaction is negligible if we have an equilibrium. We'll talk about equilibrium in a different chapter, meaning the product disappears as it's made, or we only measure the initial rates, so it's very close to time equals zero to be able to do this. We want to look at a reaction one direction. So what can we say about the rate laws below? I've got rate equals K times concentration of A over concentration of B. The way this is discussed is this is called, there's invisible ones up here. Right? We don't write ones when they're there, they're implied. So if you don't see anything there, that means it's a 1, and we say this is first order in A. It's also first order in B. And that means it is second order overall. because you've got those invisible ones, it adds up to a 2. What if I have the rate equals K times the concentration of A squared times the concentration of B? This is referred to as second order in A, first order in B, and third order overall. What does that mean? It tells me about how it's reacting. H2O2, hydrogen peroxide, can be used as a disinfectant. It decomposes as the following. 2 moles of hydrogen peroxide react to form 2 moles of water and 1 mole of O2. If the change in concentration of O2 over change in time is 0.0014 molar per second, what do you predict for the change in H2O2 over time? I've got change in O2 over change in time. I know that equals 0.0014 molar per second. I really want the change in the concentration of H2O2 over change in time. So I can use my stoichiometric ratios. I can say 0.0014 molar per second for O2. I'm going to write it down here just because we're out of space. And I see the molar ratio here. 2 moles of H2O2 react to produce 1 mole of O2. This gives me an answer of 0.0028 molar. Let me see if I can. But is that really the correct answer? Is it really 0.0028 molar? The value is right. The magnitude is incorrect. We need to put a negative sign in front because it's a reactant. It's being consumed. So the answer here is E, negative 0.0028 molar per second. What is the order of the reaction with a rate law of K times concentration of A times concentration of B squared? Order of reaction, overall order here. It's 1 with respect to A, 2 with respect to B, so overall 3. What is the reaction order with respect to reactant B if the rate is equal to K times concentration of A times concentration of B squared? With respect to is often written as WRT. So with respect to B, it is 2. If the reaction has a second order rate law, then what are the units on the rate constant? Great question. The rate itself always has units of molar per second. If something is second order, that means I either have something where it's A quantity squared, or I could have rate equal to the concentration of A times the concentration of B. Both of those would be second order. But I've got this proportionality constant in here that I need to take account of. And the units can change depending on the reaction. Rate, always, no exceptions, molar per second. If I have molarity here squared, this is equal to molar squared. I need K to do whatever it needs to do to have the correct units so that I get to molar per second. So K definitely needs to have a second in the denominator, but then I need to cancel out 1 molar. So it will be 1 divided by molar seconds, because 1 over molar second times molar squared gives me molar over seconds, which is my rate. I see the same thing here. This is molar, this is molar. I need 1 over molar seconds so that my molar and molar cancel out. I'm left with my molar squared for my rate. So your rate, your units on your K constant can change, but you need to make them match because the rate always, no exceptions, has the units molar per second. If the reaction order is 0, what are the units in the rate constant? Again, molar per second for rate. 0 order. We'll do more of this in a few slides, but 0 or in another module. But 0 order in A means that rate is equal to K times A naught. What happens when we raise something to the value of 0? Rate is equal to K. If rate is just equal to K, what must the units be? Molar per second, because they have to match to that rate.